So in the section on the second derivative test, we looked at regions, like closed and bounded regions, so like trying to find the max and min values of a function on, say, a rectangular region or a triangle. Well, sometimes in those cases it's really easy to find equations for the boundary and plug it into the function. And sometimes we can even do that for circles and ellipses. But other times we can get functions that are even more wonky than those. But I mean, even in the case of the ellipse or a circle, it can already get pretty messed up. So we can actually attack those from another perspective as well. On the boundary of these situations, we can do Lagrange multipliers. So these types of problems still split into two, sort of an inside and an outside part for finding the critical points and the potential points for extremum. But sometimes it's nice to use Lagrange multipliers on the boundary, especially if it's a messy situation. All right, so I'm actually going to start the solution over here in this video because you'll see. So we start this with an inside part, okay? Because that's usually the quickest one. All right? So remember, inside, we're talking about the inside of this region. Now remember, this region here, this is x squared plus y squared over 1/2 squared, less than or equal to 1. So this is an ellipse, right? It's a kind of tiny one. Right, so if this is x and this is y, it kind of goes out like this, where this is a half and this is 1, and the ellipse looks like this. So we have two parts. We have to find the critical points inside the ellipse, and then we have to do Lagrange multipliers on the boundary. Right? So inside, what we're doing is looking for points where the gradient of f is 0. Okay, so let's go ahead and find the gradient of f. That is minus y e to the minus xy and minus x e to the minus xy. Okay? So when is the gradient 0? So if we want the gradient to be 0, that's the same as asking that minus y e to the minus xy is 0 and minus x e to the minus xy is 0. Well, an interesting thing here is e to whatever you want is never 0. So this, we can divide out this part from both equations and get simply minus y is 0 and minus x is 0, which in other words tells us 0, 0 is a critical point. Right? So this is a point we should keep our eye on. Right? That might be one of the extrema. All right, so that's it for the inside. Actually, we should double check, is 0, 0 inside this ellipse? Not on the boundary, not outside it, but actually inside. And of course it is, right? It's the center of the ellipse. Okay, so now we need to do the Lagrange multipliers on the boundary. Right, so I'm going to section this off. Now we're going to go on the outside. Well, the boundary. So we have our function f, and actually we've even already computed the gradient. Now on the boundary is just, the x squared plus y squared equals, plus 4y squared equals 1. All right? X squared plus 4y squared equals 1 is the boundary. So that means we should use g of xy is x squared plus 4y squared, right? Because then g equals 1 is the boundary. Okay? So we already have the gradient of f, so gradient of g, it's 2x in the x component and 8y in the y component. All right, so now here comes the fun. We have to solve this Lagrange multiplier system, which is given by negative y e to the minus xy equals lambda times 2x, negative x e to the minus xy equals lambda times 8y, and x squared plus 4y squared equals 1. Okay, and I'm going to again label these 1, 2, and 3. All right, so we have to solve this system. This one's a little bit more tricky than the last one, as you can tell, because now there's an exponential in here that's kind of throwing everything off. So how should we go about trying to solve this guy? One thing here is we can start trying to look for something that the equations have in common. So in this case, they both have an e to the minus xy in it. So maybe we should try solving for that. Because if we solve for e to the minus xy in both of these, then we can set them equal to each other. All right. So in equation 1, we can do that unless y is 0. All right. So let's check what happens when y is 0. What can happen? We can use equation 2. Okay, equation 2 will tell us then that negative x e to the minus xy has to be 0, right? Because y is 0 here. Well, that leaves, actually, this nails it down even more because y is 0 up here as well. So this is the same as saying minus x e to the 0 is 0, which is the same as minus x equals 0, which means x equals 0. Well, that's a contradiction to equation 3. We have to have then 0 squared plus 4 times 0 squared equals 1, but that's not true. Right? That 0, comma 0 isn't a point on the constraint. So this, what this tells us, so therefore, y is not 0. All right? That's good news. All right? Doing this whole process again on 2, similarly, we get that x is not 0. Right? So what's the idea there? I won't write it down, but what happens is either x is 0 or it's not. If x is 0, then we go up to equation 1, and for the same reason as here, we get that y has to be 0, and again, that's a contradiction to equation 3. So what we know then is y is not 0 and x is not 0. Now it's very important to know that because what we had talked about earlier about solving for e to the minus xy in both cases, we have to divide by y in the first equation and x in the second. If either x or y is 0, we can't do that, right? And we need to do it in both equations. So, finally then, we can do the division, right? So, we have e to the minus xy. Equation 1 tells us that's equal to lambda times 2x Actually, let's leave the minus sign over here too. Just divide by the y. Okay? But this is also equal to, by equation 2, if we divide by x, lambda times 8y over x. All right, so do you see what has happened here? We now have a new equation that we can work with. This one here. So let's rewrite this a little bit. So this is the same as saying 2 lambda x squared is equal to 8 lambda y squared. All right? So what happens here now? And let's call this 4. Well, we have two choices. We can start maybe trying to see what happens with lambda. Or we can straight away take equation 3 here and get rid of one of x or y. And let's do that, actually. Because right now, this is an equation with 3 variables in it. And if we can cut down on the number of variables, that'll help. Okay? So let's go ahead and do that now. Let's plug 3 into 4. Right? But the way we're going to do that is notice that we can kind of make a 3 prime down here, which is x squared is 1 minus 4y squared. Okay? So let's go ahead and plug that in. Then we get 2 lambda x squared is 1 minus 4y squared, right, equals 8 lambda y squared. All right. So we have 2 lambda minus 8 lambda y squared is 8 lambda y squared. So this tells us that, well, 2 lambda is 16 lambda y squared, or lambda is 8 lambda y squared. All right, now we have this new guy. Let's call this 5. Right? Now, in there, this is a little bit easier to deal with now. So in here, one of two things will happen. If lambda is 0, then this is always true. If lambda is not 0, then we can get some information about y. So let's see what happens first if lambda is 0. Okay? So if lambda is 0, right? If that is true, then this equation is true no matter what. But then we go over to, let's say, equation 1. Right? So if lambda is 0, equation 1 tells us that negative y e to the minus xy is 0. Well, since y isn't 0, remember we showed that up here, okay? Since y isn't 0 and e to the minus xy is not 0, in fact that one's never 0, this is a contradiction. Right? So what that means, so therefore, lambda is not 0. What's the point of that? Well, now in equation 5, I can divide by lambda. Right? So, equation 5 will give us that 1 is 8y squared, which is saying y squared is 1 over 8. which is saying y is plus or minus 1 over 2 root 2. All right, now we're making progress. So now we just have to find the x values. So let's do both of those. And again, we of course have two cases. Y equals 1 over 2 root 2. So in this case, we plug things into equation 3. And we get, actually, it's maybe easier to even use 3 prime. We get that x squared is 1 minus, and actually in this case, notice it doesn't matter whether y is positive or negative because we're squaring it. So we can actually just put the plus minus back. 1 minus 4y squared, which is 1 minus 4 times 1 over 8. So 1 minus a half, which is a half. So that tells us that x squared, that x is 1 over root 2. So what happens here is we get 4 new possible points. Okay? So we have 1 over root 2, 1 over 2 root 2, 1 over root 2, minus 1 over 2 root 2, minus 1 over root 2, 1 over 2 root 2, and finally, minus 1 over root 2, minus 1 over 2 root 2. Right? These are possible extrema. So, as you can see here, I've kind of run out of space. So, what we're going to do is get rid of everything but the information we still need by slamming this board. So now that we only have the information left that we need, let's start plugging our candidate points into our function f and then compare the values. Okay. So if we plug in the point 0, 0, we just get, well, e to the 0, which is 1. If we plug in 1 over root 2 and 1 over 2 root 2, well, x times y, the product of these two is 1 over 2 times 2, which is 1/4. So we'll get e to the negative 1/4. Now here, since they have opposite signs, we actually get e to the 1/4. And again here, e to the 1/4. And then e to the negative 1/4 here, since they have the same sign. Right? Well, those are the f values. Right? And that's just, again, plugging them into the function here. So now we need to know, what type are they? What's the min? What's the max? All right. Well, so we get a 1 here. And then we need to know what these are. So here's where it gets a little bit interesting. How do we tell? So 1 is looking pretty big at the moment because there's a bunch of 4th roots everywhere. But, well, let's look at e to the 1/4. So remember, anything to the 0 power is 1. If the number in the exponent goes above 0, then, well, since exponential functions where the base is positive increase, that means this has to be bigger than 1. Well, if we take the reciprocal of this equation, this tells us then, so this means divide both sides, well, I guess another way is divide both sides by e to the 1/4. That tells us 1 is bigger than e to the minus 1/4. So what that tells us is these two are bigger than 1, and also, of course, bigger than this. That has to be true, since they're less than 1. So that means here we have a max and a max, and here we have a min and a min, right? And this one here, well, it's not what we're looking for. When we're extremizing, we only want the absolute max and the absolute min. This is a local something. It might be like an inflection point looking thing. It actually doesn't matter because we only want, like I said, the absolute max and the absolute min. And these are the two absolute mins. These are the two absolute maxes. Okay? So thanks for sticking around through this marathon of a problem. Hopefully it wasn't too bad. Lagrange multiplier problems can sometimes do this. And I thought it would be a good idea to give you an idea of, how to get through one of these not simple, straightforward problems. Okay? So see you in the next video.